So what we'll do today is continue our discussion of the binomial theorem and then also start talking about a related idea called Vietas formulas. Okay? But first, a few announcements. So one, homework 7 is out and it's due on Sunday, but it only consists of 3 problems. So it should be relatively short, and 2 of them are pretty much examples straight out of lecture. One you have to think a little bit about, and it's more based off of what we're going to do today. But I don't think it's an unreasonable ask to have this done for Sunday. And there will be a more involved homework on the same topics due in the fall, like the week after that. Okay, and that will be posted on Piazza. Okay, any questions logistics-wise? Okay. So remember, last class we talked about the idea of the binomial theorem, which tells us in order to expand x plus y to the exponent n, it turns out that it's equal to the sum, where k goes from 0 through n, of terms of the form n choose k times x to the exponent n minus k, y to the exponent k. Okay, we notice these coefficients all come from Pascal's triangle, right? So we expand out x plus y squared. It gives us 1 x squared plus 2 xy plus 1 y squared. 1, 2, and 1 reads you the second row of Pascal's triangle. Okay? And, knowing that in mind, you can expand really anything, right? And we'll actually go even further than just using x and y. We'll replace x and y with, other variables. And then, of course, your coefficients won't exactly be the numbers in Pascal's triangle, but that's what you'll multiply everything by. Okay? And then we also had the idea of the general term, which gave us an expression for just a specific term in the series. So we'd say t sub k, and k goes from 0 through n, so there's n plus 1 terms. Is n choose k, x to the n minus k, y to the k. Okay? And we started looking at some applications of binomial theorem and different problems that you might be asked last class, and we'll continue doing that now. Okay, so the first one was, what's the sum of the coefficients of this expression? Recall, you just substitute in the value 1, because when you have any polynomial expression, the way to get the sum of the coefficients is you pass in all of the values being equal to 1, and it will sum all the coefficients for you. So in this case, we get 3 times 1 squared minus 4 times 1 to the 12, which is negative 1 to the 12, which is 1. Okay, and we looked at that last class. Okay, we also used Pascal's triangle, we also used the binomial theorem to prove that the sum of the nth rows of Pascal's triangle is 2 to the n. And we did that by looking at the binomial expansion of 1 plus 1 to the n. And we said that this is the sum of the form where k goes from 0 to n of n choose k, 1 to the n minus k times 1 to the k. Well, 1 to the n minus k and 1 to the k are both just 1, so this really boils down to just the sum of these terms. And this, of course, on the left is 2 to the n, and we're done, basically. Okay, so we proved this exact statement, both using a combinatorial argument. Remember, we said both sides of the equation count the number of subsets of a set of size n. We can also do it using the binomial theorem. Okay, one question you may be asking is, how can we prove that the binomial theorem itself holds true? Right? And so we won't do it in lecture, but I found a nice website that goes through a proof of the statement of the binomial theorem using induction. So I can link that on Piazza and on the website. It might even be a homework question for the following week. Okay? And I'm going through this relatively quickly because we already did all of this. Then there was the idea of using the binomial theorem, or at least the first couple terms in the binomial expansion, similar to how we use a Taylor expansion in order to approximate various square roots or cube roots or integers raised to different exponents. Okay? So as an example, and the way we do that is we could rewrite terms of the form n choose k to not use any factorials, right? So we have n choose 2 is equal to n times n minus 1 over 2, right? And that you can pass in any n, so can pass in any n, not just whole numbers. Okay? Sure, it doesn't mean the same thing as n choose 2 did, right? n choose 2 had the meaning of, this is the number of ways I can select a subset of size 2, from a group of n. So what does plugging in 0.5 into that mean? It doesn't really make sense in terms of that interpretation, but algebraically, you can still compute the value. Okay, you can do the same thing for n choose 3, so on and so forth. And you can use these, like, this quote-unquote n choose 2, but in this case, we're using n being 1/3 in order to help us take the cube root of 8.03. And I write 8.03 as 8 plus 0.03. And I just use the first 3 terms in this expansion, and I get this expression, 2.002496875. But if you try this on a calculator, it's pretty close, right? Like the first, 5 or so digits, 6 or so digits, 7 actually, match, right? Up to here. All look the same, even to the 8 actually. So, very close. So any questions with how to use the binomial theorem to do these sorts of approximations? And this is one of the questions that's on homework 7, if you have already looked at it. No questions? Great. Then we also looked at the proof of this identity that we called the freshman's dream identity, right? And what we did was we looked at the expansion of x plus y to the exponent p, and we know it looks like x to the p plus p choose 1, x to the p minus 1y, plus blah, blah, blah. A bunch of stuff in the middle, plus y to the p. And what we wanted to show is that this expression over here, modulo p, is equivalent to just x to the p plus y to the p. Right? And what we did last class is we showed that each of these terms, each term contains a multiple of p. And again, how do we do that? We show that p choose I is equivalent to 0 mod p when I is not equal to 0 or p itself, and p is prime. Right? So p choose 0 and p choose p are both always going to be equal to 1. But if you look at p choose 1, p choose 2, any of those things, we showed that that will always be a multiple of p, because there will be a multiple of p in the numerator, but not the denominator, because p is prime. And all of the elements of the denominator are less than p. Okay? So any questions with this? Okay, so up until that point, that was just recap. But now, this is an example that we didn't have enough time to cover last week. Suppose we want to determine the coefficient of x to the 20 in the expansion of x to the 5 minus 5 quantity to the 7. How can we use the general term to help us? Okay, so I'll give you a couple minutes. Try and determine what the coefficient on x to the 20 in this expansion is. Of course, without, Wolfram alphaing it or writing out every single term of the expansion. So try and figure this one out. And talk to the people near you to try and do so. Okay, any ideas? How can we use the general term to help us in this expansion? Or help us determining the coefficient? Yeah?
To write out the general term,
Okay.
and then set what the exponent on x is equal to in terms of k, is that equal to 20?
Yeah. Exactly. So what we're going to do is look at the general term, like first determine it, and then take the exponent in the general term and set it equal to 20, and see what value of k we need to pass into it. Then we can just evaluate everything else in the general term, and it'll tell us the coefficient. Okay? So first let's start with the general term. We know it's going to be something of the form 7 choose k, x to the 5 to the 7 minus k, and then negative 5 to the k. Okay, and again, I'll do a little bit of simplification. I like pulling out the negative 1 to the k out front, just because you can immediately tell if the term is positive or negative. We can have 7 choose k. I'll pull all the constants out front, so we'll have 5 to the k here, right? So I rewrote negative 5 quantity to the k as negative 1 to the k and 5 to the k, and we have x to the 5 to the 7 minus k. So this ends up being 35 minus 5k. Is that clear? So we know that if we're looking at term k, the exponent on x will be 35 minus 5k. So yeah, what we can do is we can take the exponent on x and set it equal to 20. And so we have 35 minus 5k is 20. And I believe that gives you k is 3. Right? And so now how do we find the coefficient? Well, we take k is 3, plug it into the general term. We have negative 1 cubed, 7 choose 3, 5 to the 3. Okay? And of course there's an x to the 20 at the end. But the coefficient is whatever that is. Okay? And again, it's not that important to work this out to a numerical answer. We could if we really wanted to, but it's about the steps to get here. So is everyone okay with this process? Because in a little while, we're going to make it a little more complicated. Any questions? So, as a follow-up, what is the coefficient on x to the 21 in this example? X to the 21. What's the coefficient on it in this expansion? Yeah.
There is no coefficient because there is no term x to the 21.
Exactly. So now if we were instead asked, what's the coefficient on x to the 21? We would set, so I can say coefficient on x to the 21. Actually, let's just put on a new slide, copy some of this. Copy. Okay, so remember this is our general term. And so the question is the coefficient on x to the 21. Well, then we'd have to follow the same process, set the exponent equal to 21. But then you solve 5k is equal to, 14, and k is equal to 14 over 5. Why does this not make any sense? Why is this meaningless? Yeah. Yeah, right. K is the index of which term we're looking at, right? If we go back to when we define the general term, k is just 0, 1, 2, 3, ... through n. It's a whole number, right? So if we solve for the exponent and get k is 14 over 5, that doesn't mean anything. So what this is telling us is that there's no term with there's no term of the form x to the 21. And so therefore, the coefficient on it is just 0. Is that clear? So k must be element of the whole numbers. Therefore, no term with x to the 21. Therefore, coefficient on x to the 21 is equal to 0. Any questions with that? Great. So this is what I want to have you work on again amongst yourselves for a couple minutes. Suppose we have this function that is of this odd form. Determine f of 3. Okay, so I'll give you a couple minutes to try and attempt this one, and then we'll come back together. Discuss amongst yourselves what you think this is. I don't hear a lot of discussing. Okay. So of course, this function is of a very particular form. Does anyone have any ideas on how we could determine f of 3? Did anyone actually determine the numerical value of it? Any ideas? Okay. So that'll be the answer, but we'll talk about how to get there. And I mean, I think it's pretty clear that the answer is not to evaluate 8 terms of a sum. Okay. So this looks almost like a binomial expansion. You agree with that? We have the something choose k. You know, this part's the same, this part's the same. But what's weird is that we have, you know, this should, like the exponent up here, should be 7 minus k. But instead it's 6 minus k. But we have a 7 minus k down here. So what does this remind you of? The exponent is 1 less and the constant is brought down in front. What does that remind you of? Yeah, so recall the derivative of x to the n is n x to the n minus 1. Right? And that's sort of hidden here. So it turns out that this sum is the derivative with respect to x of a different binomial expansion. So let's figure out which that is. Okay, let's come over here. So we notice this part's not going to change. And just to make it a little more explicit, let's bring the 7 choose k out here. And then we have x, so we have this thing, 7 minus k, x to the 6 minus k, and then negative 1 to the k. Okay? And so the claim I will make is that this is nothing but the derivative with respect to x of this thing. Why is that a valid claim? Well, it's because everything other than this term over here is constant with respect to x. Right? If I start with what I have over here, the 7 choose k has nothing to do with the x, and the negative 1 to the k has nothing to do with the x. So when I take the derivative of each of these pieces, I can treat 7 choose k and negative 1 to the k as constants. Right? And then I just have the equivalent of some constant times x to the 7 minus k, and the derivative of that is the same constant times 7 minus k times x to the 6 minus k. Is this clear? Okay. And so now that we've established that this is the derivative of something, what is it the derivative of? Well, it's the derivative with respect to x of, actually the answer might not actually be 128, but you'll see where we're going. It's the expansion of x minus 1 to the 7. Is that clear? Okay. And then, why don't I make this a little smaller? Can you not do that in this app? Okay, whatever. We don't need it. And what is the derivative of x minus 1 to the 7? I think it's just 7 times x minus 1. So that means that's just what f of x is. So therefore, f of 3 is just 7 times 3 minus 1, which is 14. Yeah, I'm sorry. Yeah, okay. Okay, so then it's, 64 times 7, whatever that is. 8, 432, 448, 448. I think, yeah. Time to go back to AP Calc. Okay? So how many people, when we started this, thought that this is the turn this was going to take? Okay, a couple. But yeah, so the binomial theorem has a lot of different problems that you can apply the binomial theorem to, which I think is pretty cool. So any questions with this approach? Cool. And just to make it a little more explicit, if you happen to be looking at the slides later, c x to the 7 minus k with respect to x is c 7 minus k x to the 6 minus k. Great. Okay, so why stop at the binomial theorem? What about the trinomial theorem? Okay, so what if we wanted to expand something of the form x plus y plus z to the exponent n? So the first thing we could do, since addition is associative, is just treat x plus y as a single term and use the binomial expansion. Sounds good, right? So I can, just group the brackets like this, and write out the binomial expansion. But then what you'll notice is that each of the n plus 1 terms, I'll have to do another binomial expansion on each of those. Right? I'll have to then further expand x plus y to the exponent n, then further expand x plus y to the exponent n minus 1, and so on and so forth. So that's probably not the best way to go. So what's another way we can proceed? Well, we can think back to how we came up with the binomial theorem. Right? We were looking at a product, just to make it a little more explicit, if we were looking at x plus y cubed, that's just x plus y, and x plus y, what we wanted to do was choose one term from each of these brackets. Right? So we could choose 3 x's or 2 x's and a y, 1 x and 2 y's, or 3 y's. So now, we'll follow the same thought process. what we want to do is multiply one term from each of these brackets. But instead, we're looking at x plus y plus z. And so we know every term in the output will be a product of one thing from the first parentheses, one thing from the second, and one thing from the third. And the total number of things we choose has to be 3. But now we just have a lot more options, right? We could choose 3 x's, or 2 x's and a z, 2 z's and a y, one of each, so on and so forth. So now we're doing the same thing, but just the number of possibilities expands. You sort of see where I'm going with this? Okay, so maybe the next slide will make it a little more explicit. Okay, so suppose just a general term in the expansion of x plus y plus z to the exponent n contains a x's, b y's, and c z's. Okay, we know that the total number of things we choose has to be n. Right, just like when the exponent on x was n minus k, the exponent on y would be k, so that the sum of their exponents, right, n minus k plus k would be n. Because we have n parentheses, we need to choose one thing from each. Then, the total number of ways we can choose exactly a x's, b y's, and c z's is, well, n factorial divided by a factorial, b factorial, c factorial. It's equivalent to saying, just as a concrete example, what if a were 3, b were 2, and c were 2? It would be like, what if I have x, 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 y, y, z, z? How many permutations of that are there? And in this case, of course, n would be 7. Well, it would be 7 factorial divided by the number of repeats for each of the 3 letters, which we have x, y, and z. So 3 factorial, 2 factorial, 2 factorial. But we have to enumerate this over all possibilities, right? Because we can choose any number of x's. From the remaining, choose some of them to be y, and the remaining all have to be z's. Does that sound okay? Right, we know we're going to multiply n things in total, choose some number of the things we multiply to be the x. Of the remaining, choose some of them to be y's, and the remaining after all of those have to all be z's. Is that clear? So we're choosing a of our terms to be an x, from the remaining choose b to be a y, and from the remaining they sort of all have to be a z. Okay, and this is very similar, as the slides mentioned, to counting the number of permutations of something like Mississippi. You start with the total number of characters factorial and divide by the repeat, like the number of times each character repeats, factorial. Okay, and so, as I mentioned before, we were going to make it more complicated. That's what we're doing right now. Suppose we want to calculate the coefficient of x to the 4 in the expansion of x minus 3x to the negative 2 plus 4. All of that to the exponent 8. Right? Over here, we sort of gave you the recipe for the general term of a trinomial expansion. Yeah?
This is the general term. Can we use like it to create a general series like we did in the binomial theorem?
So like, how can we write this as a sum?
Yeah.
Yeah, we're getting there.
Okay.
So right here, we sort of have the blueprint for the general term of a trinomial expansion, right? And this is very similar to the same thing we had for a binomial, just we knew that if we chose k of our things to be x's, the remaining n minus k would automatically be y's. But here we have two choices, right? First, the number of things we choose to be x, and then the number of things we choose to be y. Right, so it was very similar. We just used the restriction that b was n minus a. Right. So that's why we didn't write it like that, because we know if b was n minus a, this first thing over here is just n factorial. Okay? And suppose we want to calculate the coefficient of x to the 4 in this thing. I write out the general term. Ends up looking like this. Right? I have x to the a, negative 3x squared, which is our b. Right? I can think of this as being our a, this is being our b, and this is being our c. Sorry, I should probably use x, y, and z. Okay, and so I've computed our general term, which is now of this form. And now we do the exact same thing as we did before. We want the coefficient of the terms where the exponent on x is 4. So here, what I do is set a minus 2b equal to 4. But now the difference is it's not as easy as just solving for the single variable, because now there's multiple combinations of a, b pairs that you have to look at. Does everyone sort of see the difference? Now, there's multiple pivot points you can think of it as being, right? First we choose some number of a's, then some number of b's for the y's, right? And so there's multiple variables that we can have in our exponent. So now what we have to do is determine all of the pairs of a comma b comma c where a minus 2b is equal to 4. Okay? And we have also the restriction that the sum a plus b plus c has to be equal to 8. Right? It can't be more, it can't be less. So that really restricts the possibilities. Okay, so let's try and figure out how we come up with these solutions. I know it's on the slides, but let's start on our own. What I'll do is start with a going from 0 and count upwards. Okay, because we know each of these things can either be 0, 1, 2, 3, 4, 5, 6, 7, or 8. Is that clear? Sorry, there should be a 4. So can a be 0, 1, 2, or 3? No. Why not? Well, b can't be negative, right? You might think, 0 and negative 2 works, but b, again, is an index. It's a number, a counting number, really. So it can't be negative. So the smallest value of a that works is 4, right? If you plug in 4 comma 0, you get 4 minus 2 times 0, and that's 4. So that works. Right? If you plug in 3, b would have to be negative 2, b would have to be negative 1, b would have to be negative, and 0, b would also have to be negative. Does a equals 5 work? No, because then b would have to be some fraction. Right? You can't take the difference between an odd and an even and expect it to be even. That just doesn't work. Can a be 6? Well, yeah. If a is 6, we can have b be 1, and that works. Okay, so far we've identified 4 comma 0, but we know a plus b plus c is 8, so that means c in this case has to be 4. And here we've identified 6 comma 1, and since again their sum has to be 8, this will also be a 1. And now lastly, can a be equal to 8? Well, if a was 8, then what would the value of b have to be? 2. But then that would violate this constraint, right? Because the sum a, b, and c has to be exactly 8. So that means the solution where a is equal to 8 doesn't work. So we found all of the solutions because we've enumerated through all the possibilities of a, right? We looked, manually checked, a is equal to 0 through 8. These are the only ones that work, that give b as an integer, and c being in that range. Okay, so we've gone through and found all of the possibilities, and now our job is just plug this in to the general term. So first we plug in 4 comma 0 comma 4, and we get one term of the form x to the 4. Then we also plug this in with 6 comma 1 comma 1, and we get another term. And we know when you simplify the result of this binomial expansion, or trinomial, I guess, expansion over here, you'll combine like terms at the very end. So what we have to do is add together all of the terms of the form x to the 4. And so the final coefficient is the sum of all of these intermediate ones that we found. So we found that if you plug in if you let a be 4, b be 0, and c be 4, you get 17920 x to the 4. And if you let a be 6, b be 1, and c be 1, you get negative 336 x to the 4. So the coefficient on x to the 4 in the final expansion, once you've simplified all like terms, will be the difference between the two, well, the sum really, but one's negative. So you get 17584. So I know that was a lot of steps to take in, but as a general process, okay. It's the same as when we were just looking at a single binomial. Find the general term, set the exponent on x equal to whatever you're looking for, figure out all possibilities for, in the binomial case it was k, And there's really only one possibility because it was linear. But here there's multiple possibilities. Identify those possibilities, plug them into the general term, and sum the result. It's the same process for binomials and now trinomials. Is this okay? Cool. I don't think we're going to do it right now, but there's an even further extension, which is what if you take two different binomials and multiply them together? And you want to find the coefficient in that. Okay? So that may or may not show up between now and the end of the semester, but probably not right now. Okay? And so the question is, how do we generalize this? Right? The binomial theorem, we wrote it nicely. We stated x plus y to the exponent n is this relatively nice sum. How can we do that? Well, it's much more difficult to list out the ways to enumerate all the possible values of a, b, and c manually. So what you do is just sort of use this shortcut and say, give me all pairs of values a, b, and c such that a plus b plus c is n. And the trinomial expansion is just the sum of all such terms. So it's not that fulfilling, but technically it works. Okay? And I mean, you're essentially never going to be used or asked to use this to actually expand a polynomial, right? If you were asked this, it would be to find a coefficient or figure out what you get when you plug this one thing in. But you're not going to manually expand this. Probably not for binomials, but certainly not for trinomials. Beyond n is equal to 3, for example. Okay? And I mean, this is an equivalent representation of the binomial theorem that give me all a comma b pairs such that the sum a of b is n. Well, that's what we do, right? We start off with a being n and b being 0, and we work our way backwards. Right? We go from n comma 0 to n minus 1 and 1, n minus 2 and 2, so on and so forth. And those represent the exponents up here, right? So if I look over here, we start off with a and b. We start with n and 0, but then we go to n minus 1 and 1, n minus 2 and 2, so on and so forth, until we get to 0 and n. And those are the exponents on x and y in the binomial expansion. So this is equivalent. So any questions with this? Cool. And the note posted on the website actually goes through all of this as well, if you want to look at that. Okay, so why stop at trinomial? We can define a more general multinomial coefficient. Okay? N choose k1, k2, k dot 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 through km. Okay? What does this really mean? And this, of course, assumes that the sum of k1 through km is equal to n. It's the number of ways you can choose one subset of size k, another of size k1, another of size k2, dot 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 through another of size km from a group of n items. So, for example, and this is the example that's on the next slide. What's the number of ways I can choose if we're looking at Mississippi? So MISSISSIPPI. What's the number of ways I can choose 1 M, 4 I's, 4 S's, and 2 P's from a set of 11 characters? Well, that's just 11 with 1, 4, 4, and 2 down here. And this is something you've already seen, right? And the reason there's no extra n minus k term in the denominator is because we're operating under the assumption that k1 plus, the sum of all of the k's is equal to n. So if we had the same assumption, you could say n choose k1, k2 holds. But since we know the sum of k1 and k2 has to be n, I could say this is just n factorial over k factorial, k1, n minus k1 factorial, and that's the same thing as n, choose k1. So this works, given that we have the constraint that the sum of all the things we choose has to be n. So another example of using the multinomial coefficient would be, suppose there are 70 students in this classroom. How many ways can I choose one group of 10, another group of 20, another group of 30, and then two groups of 5 from this set of people. That kind of makes sense. Actually, that's not necessarily the best example, but I like the Mississippi example for explaining this. Okay? And so, how do we formally express this? Well, just like for the trinomial theorem, there's no elegant way to write it. So you just say it's a sum over all combinations of k1, k2 through km, such that their sum is equal to n, of these multinomial coefficients. What does this product thing mean? Well, it just means x1 to the k1, x2 to the k2, dot, 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 xm to the km. Okay, and so your question will be like, what question could you ask about this? And the answer is, the point of this is not to ask questions. It's just to see, can we generalize things we've seen in the 2-element case to, for example, the 3-element case and then the general case, which is something that is an important skill, I think, to have. Okay? Here's like a mini quiz question. What's the sum of all of the multinomial coefficients with m terms? With m was equal to 2, so the sum of all binomial coefficients with a fixed n, I guess we should say, with a fixed n, right? The sum of all binomial coefficients with n being fixed was what? What was that? All the terms of the form, the sum of all the terms of the form n choose something. We did it a couple slides ago. What is this expression equal to? Yeah. 2 to the n, yeah. And so, more generally, the sum of all coefficients, all multinomial coefficients of m terms with a fixed n would be what? Like if I just had x1 and x2 here, sure, the sum would be 2 to the n. But if I have m terms down here, what would the sum be? M to the n, yeah. Because I could do the same thing, replace each of x1 through xm with a 1. And on the left-hand side, I would have m to the n. This product thingy would all just be equal to 1 because it's a product of just a bunch of 1s. And I would get the sum of all these coefficients. Okay? So again, this is a lot to take in. Highly recommend you just look at the notes, go through the slides again, and don't really expect any questions on the multinomial theorem, for example. You should know what all of these, like what the sum indexes mean, that sort of thing. You should get the general picture, I would say. Feel free to ask questions, of course. Looks okay? Great. So now we'll pivot a little bit, and we're going to start talking about this idea of Vietas formulas. Okay? So, I guess while we're still thinking about the binomial theorem, you can do the attendance. So, I'll give you a minute or two to fill that out, and then we'll proceed. Okay, let's continue. And just feel free to keep filling it out if you haven't. Okay? And so, before we proceed, a fact that we sort of need to establish, a polynomial of degree n, so something of the form, I don't know, p of x is x to the n, what am I doing? A sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 a sub 2 x squared plus a1x plus a naught. That's a polynomial of degree n, and it has exactly n roots. Okay, in previous classes you might have seen, the parabola has 3 different cases. One where it sits on the axis, one where it crosses the axis, and one where the vertex is above the axis or below. This sort of seems familiar. And here you would have seen the first one has 1 root, the second has 2, the third has 0, right? In reality, all 3 of them actually have 2 roots, but some of them may be repeated and some of them may be complex. So in general, you can say a polynomial of degree n has exactly n roots. So here it's just a double root. Here they're both complex. Is that okay? And that's all we really need to establish with regards to that point to move forward. And so Vietas formulas give us a way to interpret a polynomial in standard form in terms of its roots without having to find the root specifically. And so I guess the motivating question is, in this polynomial, p of x is ax squared plus bx plus c, and we're assuming that all of the coefficients are real numbers. What is the sum of the roots of the polynomial, and what is the product of the roots? If p of x is ax squared plus bx plus c, what is the sum of the roots and what's the product of the roots? Well, you may be asking, we don't know what the roots are, so how can we figure it out? But it turns out there's a way, just by looking at this, to figure out what the sum and product of the roots are. And let's look at that. So, if we want to find a formula for this in general, for example, we'll look at p of x, ax squared plus bx plus c. We can use our trusty friend, the quadratic formula, and sum and multiply the expressions for R1 and R2. If we say the polynomial has 2 roots, R1 and R2. Okay, so I say R1 is the one where in the numerator you take the plus, and R2 is the one where you take the minus. Really doesn't matter. And then you sum them. The discriminant, I believe is what they call it, cancels out, and you're left with negative b over a. Okay, and when you multiply R1 and R2, a lot of things end up canceling out as well, and you get c over a. Okay, so what does that tell us? Given just this polynomial, p of x is ax squared plus bx plus c, doesn't matter what a, b, and c are, the sum of the roots is negative b over a, and the product of the roots is c over a. Okay? And you don't need to find the roots themselves. So for example, why don't we look at 2x squared minus 7x plus 15. What's the sum of the roots in this polynomial? What is the sum of the roots? Any ideas? Yeah. 7 over 2, right? So one thing that I'll warn you of moving forward is be careful of the negative, because notice here it's negative b over a, but there's a negative here. So it ends up being positive, like negative, you get what I mean, 7 over 2. And then the product is 15 over 2. Okay? And actually, depending on how you learned how to factor things, if you looked at, for example, x squared minus 6x plus 5, back in the day, you might have learned this as trying to find two numbers such that they So they multiply to 5 and add to 6. Right? And then, the roots in that case are 1 and 5, so you have x minus 1 and x minus 5. Okay? But, we use the quadratic formula here. What if we wanted to do this for polynomials of degree 3 or 4 or 100? Right? This is all about generalizing this to an arbitrary degree. We can't use the quadratic formula there. So what can we do? And so let's approach the degree 2 case a little differently. Okay? And so what I'll say is, again, suppose p of x has two roots, r1 and r2. Okay, so I'll say p of x is a times x minus r1 and x minus r2. Okay, why does this make sense? Well, if I plug in p of r1, I get 0. Plug in p of r2, I also get 0. Why do I have the a out in front? Well, it's because, given that you fix the two roots, you can stretch the polynomial as much as you want. So you just need to account for that. But in a lot of the cases that we'll look at, a will just be set to 1. But just to be a little more general, I can, any polynomial, you say it has two roots, r1 and r2, I can express it in this form. Are you okay so far? So now what we can do is just expand this. And remember, we're trying to compare this to ax squared plus bx plus c. Well, let's expand. So we have a, and then now we have a similar problem as when we looked at the binomial theorem. I know every term in this output will be a product of one thing from the first parentheses times another thing from the second parentheses, right? And so there's three cases, right? I could choose 2 x's and 0 of the r's. I could choose 1 of the x's and 1 of the r's, or none of the x's and 2 r's. The only way this is different than the binomial theorem is that before, all of the things we were multiplying together were all the same. Now they're not necessarily. We have x minus r1 and x minus r2. Okay, so in the first case, if we multiply the two x's, we'll have x squared. In the second case, if we multiply one x and one of the r's, I'll have plus x times negative r2. Right, so I get this multiplication, right? And then plus x times negative r1. And then there's the last case where I just multiply the two r terms together. So I have plus negative r1, negative r2. Is this okay? And now I can distribute this negative sign and collect like terms. So I have a x squared minus r1 plus r2, x plus r1, r2. Because we have the double negative at the end. Is this okay? And then now, distribute the a. I have ax squared minus a r1 plus r2x plus a r1, r2. But we know what we want to compare this to is really ax squared plus bx plus c. And now we start to see the similarities with the result that we already found. Comparing the two a's doesn't really tell you anything, but we notice negative, what are we doing over here? Negative a times r1 plus r2 has to be b. But r1 plus r2 is just the sum of the roots, which is what we're looking for. And we notice a times r1 times r2 has to be c. Okay? So we notice b has to be negative a times r1 plus r2, which implies that the sum of the roots is negative b over a. And similarly, c has to be a times r1 times r2, which gives us the product has to be c over a. Okay? And so this is nothing new because this is exactly what we just determined over here. But we approached it a different way, and the way we approached it will allow us to extend this to polynomials of degree 3, 4, or an arbitrary degree. Is that okay? So, this just repeats that. Now, let's do exactly that. How can we approach the same thing for polynomials of degree 3? And of course, we could sit there and just try and expand this out, x minus r1, x minus r2, x minus r3, by first combining the first bracket, right, and then multiplying that by x minus r3. But we can go about it a little more efficiently, right? And so what I'll do is we'll say p of x is now a times x minus r1, x minus r2, and x minus r3. So I'm saying p of x is now a cubic polynomial, so a polynomial of degree 3 with 3 roots, r1, r2, and r3. And of course, the thing we're going to compare this to is if we used, the standard coefficients, like for example, ax cubed plus bx squared plus cx plus d. It doesn't really matter what we call these. Usually it'll be a little more clear once we hash this out. But we can keep that in mind for now. And so now what we need to do is expand out this expression for p of x. Okay, so p of x is equal to a times. Now again, as I was mentioning, we know what x minus r1 times x minus r2 will be, because we looked at it in the last slide. X squared minus the sum of the roots times x plus the product of the roots. And then I could go and multiply that thing by x minus r3. But again, that's not an efficient process, because when I go to the case of we have a degree 4 polynomial, I'd have to combine x minus r1, x minus r2, multiply that by x minus r3, and then multiply that again by x minus r4. So it's not sustainable. We need to figure out a better way to approach this. And so we'll go back to this argument. Remember, each term in this expansion will be a sum of one term from here, one term of here, and one term, a product, sorry. One term from each of these 3 parentheses. Just like in the binomial theorem. Is that okay? And so, there are a couple cases to look at. We could choose 3 x's and none of the roots, 2 x's and 1 of the roots, 1 x and 2 of the roots, and 0 x's and 3 roots. Those are our 4 cases. Okay? So the first case, we multiply 3 x's together, we get x times x times x, x cubed. Then the next case, we'll be multiplying 2 x's and 1 of the roots. So I know whatever I get will be plus x squared times something. Because I'm multiplying 2 of the x's and something else. Right? If I multiply if I multiply the x's from the last 2 parentheses and the root from the first one, I'll get negative r1. If I instead, multiply the x's from the first and the third, I'll get negative r2. And then if I lastly multiply the x's from the first and second parentheses, I'll get negative r3. And those are the 3 cases, right? How do I know those are the 3 cases? Well, because if I have 3 parentheses and I want to choose 2 x's, there's 3 ways to do that. So it all comes back to this. Okay? And so let's continue. So the next case is when I have an x and then I multiply 2 of the roots together. So now how are all of the ways I can multiply 2 of the roots? Well, I could multiply the first and the second, so I could have r1 times r2. I can multiply the first and the third, so r1 times r3. Or the second and the third, so r2 times r3. And notice, since the roots, we have them written as negative r1, when I multiply an odd number of them, the sum will be still negative. If I multiply an even number of them, the sum will be positive. Is that clear? Okay. So I have x, so I can multiply the first 2, or the first and the third, or the second and the third. And then in the last case, I just multiply all 3 of the roots together. So there, I would just have negative r1, negative r2, and negative r3. Is that clear? And then, so cleaning this up a little bit, we get a times x cubed minus x, usually you write the coefficient first, so minus r1 plus r2 plus r3 x squared plus r1 r2 plus r1 r3 plus r2 r3 x minus r1 r2 r3. So we've expanded this thing out, but notice we didn't do a lot of mechanical calculations. We just reasoned about it and were able to get to the answer, which is something that's important. And it's especially important because we could just follow the exact same process if we wanted to do this for a degree 4 polynomial or a degree 5 polynomial. You don't have to sit there and just multiply binomials. We can do this a little more efficiently. And so you notice the coefficients, we have the sum of the roots right here. We have the product of the roots at the end, but then now the coefficient on x is something else. It's this weird looking thing, r1, r2 plus r1, r3 plus r2, r3. It's the sum of all possible ways you can multiply two of the roots together. Okay? And so each of these is what we refer to as a symmetric sum. Why is it symmetric? Well, because if you replace the order of any of them, it doesn't change. It's symmetric in terms of all of the variables you're given. Okay? So to formalize that a little clearer, when we're multiplying out these parentheses, again, there's 4 cases we could look at. The number of x's really, right? We choose 3 x's or no roots, 2 x's and a single root, 1 x and 2 roots, or 0 x's and all roots. And we do that expansion, and we get these expressions. Okay, I'll remove the highlight just so it's a little easier to read, but we get that. So we get that the sum of the roots is negative a2 over a3. And so what's a2 and a3? Well, a sub k is the coefficient of x to the k. Okay, so notice here, a3 is the coefficient of x cubed, a2 is the coefficient of x squared, and so on and so forth. So, as an example, suppose we're given p of x is, 3x cubed minus 14x squared plus 7x minus 12. What's the sum of the roots? Yeah. Good, 14 over 3. So the sum of the roots, and this is the biggest thing you probably have to remember, is always negative the coefficient of the second highest term divided by the coefficient of the highest term. So if we instead had, a polynomial of degree 100, the sum of the roots would be negative the coefficient on x to the 99 divided by the coefficient on x to the 100. Is that clear? This pattern will keep on repeating, and no matter what, the sum of the roots will be the negative of the coefficient of the second highest term. Is that clear? And then what's the product of the roots? Well, the sign of the product alternates. Right? So remember, in the degree 2 case, r1 times r2 is just the last coefficient divided by a. But in the degree 3 case, it's negative. And that's because the polynomial itself is of odd degree, right? And the signs alternate, right? So here we have this first term is negative, then positive, then negative. So in this case, for the product of the roots, you'd have to take the negative. But if we looked at degree 4, the product of the roots, you wouldn't have to take the negative. Okay, so the product of the roots in this case is negative 12 over 3, which looks like 4. Okay? And sure, it's useful to look at arguable how useful it is to look at a polynomial and determine what the sum and product of the roots is. But what we'll really use this for is some other types of problem-solving techniques where maybe we don't have some of the coefficients, or maybe we're trying to find some specific property about a root. Okay, just looking at a polynomial and reading off this information on its own is not that useful. Okay, and so this makes it a little more clear. As an exercise, I guess we wanted you to determine this for polynomials of degree 4, but they sort of worked that out for you. All right, so the first term will be the sum. Then you'll have the sum of all possible ways you can multiply two of them and add them together, right? And notice, how many ways can you just add one of them together? Well, 4 choose 1. How many ways can you choose 2 of them to multiply? 4 choose 2. How many ways can you choose 3 of them to multiply? 4 choose 3. Okay, so this is going to keep showing up, this idea of choosing things. Okay, and then, in true fashion of this lecture, I guess, we can generalize it to arbitrary degree. Okay? Sure, we could assign some weird notation to this if we wanted to, but this formula on its own is not that useful. It's about recognizing the pattern. Okay, it's not about copying down a formula and using it. Is this okay? So here's a question. What's the sum of the roots of the following polynomial? What's the sum of the roots of that polynomial? Okay, it can't be anything meaningful because I just made some random numbers up. So what is it? Starts with a Z. So why is it 0? Can anyone tell me why it's 0? Yeah, the coefficient on x to the 99 is 0. And remember, in all of these cases, the sum of the roots will always be negative the coefficient of the second highest degree term divided by the coefficient on the highest degree term, no matter what the degree is. Right? And so since the x to the 99 term has coefficient 0, the sum of the roots is 0. And I'm telling you that's a big part of solving number 3 in the homework. Okay? I'm pretty sure it even tells you that in the question. So is that clear? So that's one thing you definitely have to pick up on. Cool. And so one interesting thing to note is that the binomial theorem is actually just a special case of Vietas formulas when all of the roots are equal. Okay? So for example, pretend we had a polynomial of degree 4 where all of the roots were equal to c, where c is some constant. Well then, when we look at all of these symmetric sums, right, the sum of 4 of the roots, well that's just 4 times c. The product of all possible ways I can multiply 2 of them, well there's 6 possible ways I can multiply 2 of them because I have 4 choose 2. And all of those would give me c squared. Right? And then the a1 would be the negative of the sum of all possible ways I can multiply 3 of them. Well, how many ways can I choose 3 of them to multiply? 4 choose 3. And so you notice this ends up being the exact same thing as the binomial theorem when all of the roots are equal. So the binomial theorem is just a special case of the Vietas formulas. Is that okay? So questions with this? So it's kind of cool how this is all related, right? We started back with just Pascal's triangle and the idea of arranging people in a line, but it can bring us to all of this. Okay. So with the remaining time, I want to walk through a couple examples of contesty style questions that you can do with Vietas formulas. I think, sure, maybe this specific question won't appear in future classes, but the thought process we'll use to solve these kinds of things will certainly appear. Okay, so don't think so much about, is Vietas formulas going to appear in the future? It's more about, is this thought process, am I going to have to do this again? And the answer to that, without question, is yes. Okay, so suppose A and B satisfy x squared minus 18x plus 18. To be a little more clear, there should be an equals 0 there. Determine a squared plus b squared. So I'll give you a minute or two to try and hash it out. Okay, so out of interest of time, we'll move on. But, so, to get things out of the way, I'm not implying that Vietas Formula is necessarily the best way to do this every time. In this question, it will be. But suppose this instead read x squared minus 11x plus 18. Well then, you see that 2 and 9 multiply to 18 and add to 7, so you know the roots are 2 and 9, and you just look at 4 plus 81 is 85. So there, like if you can easily factor it, you don't have to go and pull out the big hammer, right? That was a weird analogy, but you get what I mean. Okay? But this is actually not factorable, the example we have. So, how can we use Vietas formulas? Well, we know that the sum of the roots is what? 18. And the product of the roots is also 18. Well, what can we expand to give us this in terms of what we already know? Well, what if we look at a plus b quantity squared? Right? What do we get with that? We get a squared, 2ab, b squared. Now we have what we're looking for on the right-hand side, a squared plus b squared. On the left-hand side, we have a plus b quantity squared minus 2 times ab. But we know a plus b and a times b. A plus b is just 18. And a times b is also just 18. And we're done. So 16 times 18, 17 squared minus 1, 100 and 200 or something. Whatever. 288. So notice we solved the question without figuring out what a and b themselves are. You don't really need to know what a and b are for this question. It's not asking it. Does this sort of make sense? So we use the properties of what we know through Vietas formulas and use it to guide us to the answer without being too messy. Right? This didn't take very many steps. Okay? Probably do one more example today. So suppose p of x is x cubed minus ax plus 15. And suppose it has 3 real roots, 2 of which sum to 5. What is the absolute value of a? Okay, so before I give you another minute or so to try and attempt it, we're told 2 of the roots sum to 5, correct? What does the third root have to be? It's the same trick when I had the 17,000 to the 55x to the 100. What does the third root have to be? Yeah, negative 5, right? Because we know 2 of the roots sum to 5. The third one has to be negative 5 so that the sum of the roots is 0. Because notice, there's no coefficient on the x squared term. Right? So we know 2 of the roots add to 5. Third one has to be negative 5. Okay? Take another minute, try and work it out, and then we'll talk about the solution and call it a day. Okay, let's walk through it. Let's make that a little cleaner. Okay, so this one, what's happening? Okay, here we go. So as we established, the third root has to be negative 5, since the sum of the roots has to be 0. But we also know that the product of the roots is negative whatever the last coefficient is, right? Because the polynomial is of odd degrees, so for the product, we have to negate whatever we see. So we have the product of the roots is negative 15. And so then, remember the coefficient on the linear terms, the coefficient on x, is this weird looking thing, right? Where we take the product of two of them at a time and sum it together. So we know negative a is this weird thing, r1, r2 plus r1, r3 plus r2, r3. Right? But then, using some clever tricks, we can factor an r3 out of the last two terms, and then then we can rewrite it as r3 times r1 plus r2 plus r1, r2 at the very end. Okay? And then the whole goal is to try and rewrite this in terms of what we know, right? And well, we know r1, r2 is just r1, r2, r3 divided by r3. Well, why does that matter? Well, because we already know definitively what r3 is, and we know what the product of the roots is because it's negative 15. We can see the last coefficient, and we also determined what r3 was, negative 5. So I can replace r1, r2 with r1, r2, r3 over r3. And then similarly, let's declutter this a bit, I know both r1 plus r2 and r3. So now in this last expression, I know everything. I know r3, I found out it was negative 5. I was told the sum of the roots, r1 plus r2, is also 5. I know r1, r2, r3, it's negative 15. And I know r3 on its own, negative 5. So I plug in all the values we know, and you get negative a is negative 22. Absolute value of a is 22. Okay, so I believe the note also walks through this exact same thing. So I think that's it for today. Remember, the homework is due on Sunday at midnight, and then we'll continue with this discussion on Tuesday.